This is Lecture 2, Collecting, Measuring, and Describing Data. By the end of this lecture, you should understand how to construct a conceptual definition, understand how to construct an operational definition, understand how to construct a good variable, be able to classify a variable's level of measurement, be able to calculate the mode, median, and mean of a variable, and interpret the variance and standard deviation of a variable. In the previous lecture, we talked about theory building and deriving hypotheses. In this lecture, we will talk about how to collect data to help us provide empirical support for our hypotheses. In the previous lecture, we talked about variables in an abstract sense. In this lecture, we are going to be more concrete about what we mean when we use the term variable. All variables have a unique name. No two variables should share a name. Otherwise, we would get confused on what a variable is measuring. In addition, all variables take on numeric values. Defense spending, for example, would be measured in dollars. With other variables, we would assign values. For example, if we had a variable that measured voters' ideology in the US, we could assign 0 to liberals and 1 to conservatives. Last, all variables should take on at least two values, such as 0 or 1. But ideally, our variables should take on more than two values. In the previous example, I said we could have a variable that measures ideology in the US, where we would assign 0 to liberals and 1 to conservatives. While this variable would identify the basic differences between liberals and conservatives, it does not tell us how liberal a voter is or how conservative they are. It also does not take into account whether a voter is moderate. A better measure could be if we had a variable that ranged from very liberal, a value of 1, to very conservative, a value of 5. This variable would give us more information about a voter's specific ideological leanings. Now that we have a basic idea of what a variable is, I'm going to talk about how we construct variables. Every variable begins with a concept. In the hard sciences, scientists often have a concrete idea of what they are measuring. They measure concepts such as temperature, volume, speed, and changes in chemical compositions. In the social sciences, we generally study mental constructs about our social environment that we know exist, but we generally do not think about in concrete terms. The first step in creating a variable is defining what we specifically mean when we use these terms. For example, we understand that there are differences between being a liberal and being a conservative, but what exactly are those differences? Liberals are more likely to support government intervention into the economy and are pro-choice, while conservatives want a limited government role in the economy and are pro-life. An alternative example is war versus peace. How do we know if two countries are at war? Generally, we expect at least one of those countries to use violent force against the other country in order for it to count as a war. Well, what if no one dies as a result of that use of force and the conflict ends quickly? If that were the case, political scientists generally would not view that as a war. It would be more like a minor dispute between two countries. As you can see, it is not always easy to define social constructs. So the first step in creating a variable is creating a conceptual definition for our variable. First, a conceptual definition defines a concept's measurable properties. For example, if we are going to measure how liberal or conservative a voter is, we would have to be able to measure their opinions on government intervention in the economy. This is a measurable property. We could conduct a survey and ask voters about their political views. Next, the conceptual definition specifies our variable's unit of analysis. The unit of analysis just tells us who the subjects are in our study. It tells us who or what they are, where they live, and when they existed. Our subjects could be individuals or states, or even legislatures or parties. We can focus on subjects in 1 year or many years. For example, if we were going to conduct a survey to measure voters' political ideology, we would have to identify which voters we would want to focus on. If we only cared about measuring ideology in the United States during the 2016 presidential election, then our unit of analysis would be voters in the U.S. in the year 2016. After we identify our unit of analysis, we can classify our data set based on our unit of analysis. Our data set would be a case study, a cross-sectional data set, a time series data set, or a cross-sectional time series data set. If we only have one subject in our data set with one or a few observations, we would have a case study. If we only have one subject over multiple time periods with multiple observations, we would have a time series data set. If we have multiple subjects in one time period with only one observation, we would have a cross-sectional data set. If we had multiple subjects in multiple time periods with multiple observations, we would have a cross-sectional time series data set. Imagine we were interested in measuring military spending. If we only focused on measuring military spending in the U.S. in 2014, we would have a case study because we only have one subject, the U.S., in one time period with one observation, 2014. If we focused on measuring military spending in the U.S. from 1950 to 2014, then we would have a time series data set because we would only have one subject, the United States, over multiple time periods with multiple observations, 1950 to 2014. If we focused on measuring military spending in all countries throughout the world in 2014, we would have a cross-sectional data set because we would have multiple subjects, all countries in the world, in 1 year with one observation, 2014. If we focused on measuring military spending in all countries from 1950 to 2014, then we would have a cross-sectional time series data set because we would have multiple subjects, all countries throughout the world, in multiple time periods with multiple observations, 1950 to 2014. After we identify the measurable properties of our concept and identify its unit of analysis, we would write down the conceptual definition of the concept. This template could help you write a conceptual definition. The concept of X is defined as the extent to which subjects exhibit the characteristic Z. If we wanted to measure how conservative voters are in the 2016 presidential election, we could write, the concept of conservativeness is defined as the extent to which voters in the 2016 presidential election exhibit the characteristic of supporting limited government intervention in the economy and pro-life policies. Of course, this seems awkwardly worded, but it includes all the relevant information you need to write a first draft of the conceptual definition of your variable. Later on, you would rewrite the sentence to make it flow better. For example, you could write, in this study, I am examining the conservativeness of voters in the 2016 presidential election. I measured the extent to which voters supported limited government intervention in the economy and pro-life policies. After we write our conceptual definition, the next step is to write the operational definition. The operational definition tells us how we specifically quantify or measure our variable. First, the operational definition tells you how you code and measure your variable. It tells you what you have to specifically view in the real world to measure a variable. It also tells you the specific values your variable takes. For example, if we wanted to measure war in 2015, we could say that a country was at war if they were involved in a violent conflict with another country that resulted in 1,000 battle deaths or more in the year 2015. We could assign a 1 to countries that met this criteria and 0 to countries that did not meet this criteria. In our operational definitions, we also have to identify our data sources. There are many places we can find data. We could conduct a survey or experiment. Alternatively, we could rely on data that other scholars have already collected, known as secondary data. After you have collected your data, the first step in analyzing your data is describing the basic characteristics of the variable. The first characteristic you need to take into consideration is your variable's level of measurement. It tells you more about the meaning of the values that your variable takes. Based on what values your variable can take, your variable is either a nominal level variable, ordinal level variable, interval level variable, or ratio level variable. Nominal level variables give us the least amount of information, while ratio level variables give us the most amount of information. An easy way to remember the order in which these classifications give us the least to most information is the French word for black, noir, N-O-I-R. Nominal, ordinal, interval, and ratio. In a nominal level variable, we divide our subjects into different categories. The categories are exhaustive in the sense that we included all possible categories. The categories are also mutually exclusive. If a subject in our dataset can fit in one category, they cannot fit in another category. For example, if we wanted to measure someone's marital status, we can place them in 4 potential categories: single 0, married 1, divorced 2, or widowed 3. The variable includes all possible categories, and a subject cannot be in more than one category. Note that while there is a numerical difference in these categories, 0 versus 1 for example, these categories do not have any inherent order. While 1 might be numerically greater than 0, married people are not inherently greater than single people, and widowed people are not greater than divorced people or married or single people. Since there is no inherent order in this variable, it is a nominal level variable. In an ordinal level variable, we divide our subjects into different categories. The categories are exhaustive in the sense that we included all possible categories. The categories are also mutually exclusive. If a subject in our dataset can fit in one category, they cannot fit in another category. For example, we could ask survey respondents the extent to which they support a candidate. They could answer strongly oppose -2, oppose -1, neutral 0, support 1, strongly support 2. Note that there is no inherent order in these categories. Strongly support 2 is greater than just support 1. However, the actual spaces between these categories are not fixed. An individual survey respondent, for example, might see a small difference between strongly opposing and opposing a candidate. However, they might see a large difference between supporting and strongly supporting a candidate. Since this variable has inherent order, but the spaces between the categories are not fixed, it is an ordinal level variable. Interval level variables have order, and the spaces between values are fixed, but they do not have a true 0. An example could be an ideology variable that ranges from -100 to 100. 0 in this variable has no real meaning, since we could have simply made the scale 50 values back and had a scale from -150 to 50 as well. Ratio level variables have order, the spaces between values are fixed, and they have a true 0. An example could be military spending. It could range from a true value of $0 to any positive dollar value. Note that ratio level variables give us the most information about our subjects. In this example, we know exactly how much a country is spending on its military. The next characteristic of your variable that you should be interested in is your variable's measures of central tendency. The measures of central tendency tell us the average or typical case in our variable. There are 3 ways to measure central tendency: mode, median, or mean. The mode is a variable's most common value. The median is the observation that takes on the middlemost value when ranking the observations from lowest to highest value, and the mean is just another word for the arithmetic average. In order to demonstrate how to calculate a mode, median, and mean, I'm going to use Commonspace scores from the 106th Congress. Commonspace scores measure each House member's ideological position on the liberal-conservative ideological spectrum. The variable is based on how House members vote on bills. The variable hypothetically ranges from -1 to 1, with numbers less than 0 being liberal scores and numbers greater than 0 being more conservative scores. So to calculate a mode, you arrange the observations in your variable from the smallest value to the largest value, and then look for the most commonly held value in the dataset. Or in other words, we look for the value in the dataset that repeats itself most often. I arranged the Commonspace scores from smallest to largest and found two modes in the dataset, one for Democrats and one for Republicans. For Democrats, there were six observations that took on a value of -0.374. For Republicans, there were 6 observations that took on a value of 0.359. No other value in the dataset repeated itself more than 6 times. The median is the middlemost value in the variable. First, we arrange the data from the lowest value to the highest value. Then we look at the observation that is the middlemost observation, with 50% of the observations below it and 50% of the observations above it. In order to find the median by hand, we arrange the data from the lowest to highest value. Then we calculate the median observation number. The position of the median is the number of observations plus 1, and that value divided by 2. So I arrange the Commonspace scores from the lowest to highest value. Then I calculate the position of the median observation. We have 437 observations. 437 plus 1 is 438, and 438 divided by 2 is 219. So we should look for observation 219 for our median value. Observation 219 takes on a value of 0.137. So the median is 0.137. The median Commonspace score tells us who controls the House of Representatives. Recall that values greater than 0 indicate House members are more conservative. If our median member or middlemost member is conservative, then it is likely that Republicans control the House in this Congress. In the previous slide, I taught you how to calculate the position of the median observation when you have an odd number of observations. When you have an even number of observations, it is slightly different. To calculate the position of the median observation, first you take the number of observations plus 1 and divide that number by 2. So if we have 436 observations, added 1 to 436 and divide that value by 2, we would get 218.5. There is no 218.5 observation. Instead, there are observations 218 and 219. What we do then is take the average of the values from observations 218 and 219. So if you look at the previous slide, observation 218 takes on a value of 0.135, and observation 219 takes on a value of 0.137. The average of 0.135 and 0.137 is 0.135 plus 0.137, and that value divided by 2, which is 0.136. Last, the mean of a variable is simply the arithmetic average, or in more specific terms, it is the sum of a set of observations divided by the total number of observations. When we denote a mean of a variable in statistics, we use the symbol x bar. Uppercase sigma indicates the sum of a set of values, and n indicates the number of observations. Applying this to our Commonspace scores example, the mean would be the sum of the Commonspace scores divided by the total number of observations. The sum of the Commonspace scores was 21.788. The number of observations was 437, so 21.788 divided by 437 is 0.05. So when should we use the mode, median, or mean? Which is the best measure of central tendency? The answer is, it depends. Here are some general rules to follow. If you have a nominal level variable, you should always use the mode. The median and mean do not make sense with a nominal level variable, as the median and mean assume a variable's values have order and a nominal level variable has no inherent order. With ordinal level variables, the mode and the median are the preferred measures of central tendency, but you can use the mean. Last, with interval and ratio level variables, if the variable has multiple modes, like the Commonspace scores did, use the modes. It demonstrates that there is not one single typical case in the data. Instead, there are multiple typical cases in the data. If, on the other hand, the mode, median, and mean are about equal, just use the mean. If the mean is significantly greater than the median, or if the mean is significantly less than the median, then use the median. As I will demonstrate in the last part of the lecture, if the mean is significantly greater than or less than the median, that means that there are major outliers in the data. In other words, while most of the observations in the dataset have similar values, there are a handful of observations in the dataset that take on extreme values. If that is the case, the middlemost value in the dataset, or the median, gives us a better idea of what the typical case in the data looks like. Of course, these are all general rules on which measure of central tendency to use. You should examine your variable closely to determine which measures you use to reflect the typical case in your dataset. The last characteristic of your variable that you should examine is how your variable is distributed. Note that this discussion only applies to ordinal, interval, and ratio level variables, as these variables assume order. The distribution of your variable can tell you a lot about the values your variable typically takes on. Imagine you have two different variables with a similar mean, but with different distribution. You have a variable where there are 3 5s, a 0, and a 10, and the average is 5. And you have a variable with 2 zeros and 2 10s, and the average is also a 5. But in the first variable, most observations are clustered around the mean of 5. We would say there is very little variance in this variable. While in the second variable, most observations are dispersed away from the mean of 5. So we would say there's a lot of variance in this variable. As you can see, these are very different variables, and just knowing the mean is not enough to tell us what the typical case is in this data. Dispersion also tells us a lot about the values the observations take. One way to illustrate the dispersion of your variable is a bar graph or a histogram. In each type of graph, on the x-axis, you place the values, or range of values if you're making a histogram, for your variable, and on the y-axis, you indicate the percentage of observations that take on those values. Here is an example of a histogram. The range of values are on the x-axis, and the percentage of observations that take on those values in the dataset are located on the y-axis. As you will see in the next couple of slides, data can be distributed in many different ways. So in this example, we have a normally distributed variable. As we will discuss later in the semester, normally distributed data looks like a bell curve with a peak in the middle and with two symmetrical halves, as in the lower end of the graph mirrors the higher end of the graph. Next, in this example, we have an example of a clustered variable and a dispersed variable. On the left-hand side image here, about 28% of the observations take on a value of 45 to 50, and the observations tend to cluster around the mean of 50. On the other hand, on the right-hand side of the graph here, only about 18% of the observations take on a value of 45 to 50, and the observations tend to be dispersed away from the mean of 50. So we would say the variable on the left is clustered, while the variable on the right is dispersed. Another way variables can be distributed is either with a negative skew or a positive skew. A variable becomes skewed when there are major outliers in the data that affect how the data are distributed. A variable has a negative skew when the mean is less than the median. This means that there are a handful of observations in the variable that take on extreme low values, and they are dragging the mean in a negative direction away from the median. Here is an example of a variable with a negative skew. As you can see here, most observations are clustered here, but there are a few observations down here that are pulling the mean in a negative direction. As a result, the mean, 13.3, is less than the median, 14.5. A variable has a positive skew when the mean is greater than the median. This means that there are a handful of observations in the variable that take on extreme high values, and they are dragging the mean in a positive direction away from the median. Here is an example of a variable with a positive skew. As you can see here, most observations are clustered here, but there are a few up here that are pulling the mean in a positive direction. As a result, the mean, 26.2, is greater than the median, 25.5. Last, a variable can have a bimodal distribution as well. This happens when the variable has two modes. Here is an example of a variable with a bimodal distribution. As you can see, there are two modes, 50 and 150. About 10% of the observations take a value of 50, and 10% of observations take on a value of 150. 50 and 150 are the most commonly repeated values in the dataset. A more sophisticated way to measure dispersion is the variance, S squared, and standard deviation, S, of a variable. The variance and standard deviation of a variable give you a specific numerical value to identify how dispersed observations are in your dataset. I do not expect you to know how to calculate the variance and standard deviation in this class. However, I do expect you to know what these statistics mean and how to interpret them. So I'm going to tell you how they are calculated to give you an idea of what they mean so you know how to interpret them. The variance is calculated by subtracting the mean of the variable x bar from each individual observation value, xi. This tells us by how much an individual observation's value deviates from the mean of a variable. If an individual observation takes on a value close to the mean, this calculation should produce a value that is close to 0, meaning a small deviation from the mean. If an individual observation takes on a value far away from the mean, this calculation should produce a value that is far away from 0, meaning a large deviation from the mean. Now we want to know, on average, how far away these individual observations' values are from the mean. We could take the arithmetic average here by adding all these observations' values together and dividing by the number of observations. However, if we did that, the negative values would cancel out the positive values, and so we would lose information. Instead, we square the values here to get rid of the negative numbers. Then we take those values, add them together, and divide by the number of observations minus 1. This is a calculation that is very close to the arithmetic average. What the variance tells us is the average squared deviation from the mean. A squared deviation, however, is not useful information because when we squared the deviations from the mean here, it made them larger, making it look like the observations deviated much more greatly from the mean than they actually did. To bring the variance back down to a more realistic value, we simply take the square root of the variance. This calculation is called the standard deviation. It approximately tells us, on average, how often does each observation deviate from the mean. While you may not have to know how to calculate the standard deviation of a variable in this course, you have to know how to interpret it. Basically, you have to know how to interpret the mean and standard deviation of a variable using this template. The mean of the variable was x units. Observations deviated from the mean of x by standard deviation units on average. For x, you literally just insert the value of the mean of the variable. For standard deviation, you literally just insert the value of the standard deviation of the variable. Last, if your variable has a specific unit of measurement, you would exchange the word units for that specific unit of measurement. For example, if your variable is measured in dollars, you would say that you would say dollars on average instead of units on average. If your variable does not have any specific unit of measurement, just use the term units. To provide an example of how to interpret the mean and standard deviation of a variable, I calculated the mean and standard deviation of the Commonspace scores from earlier in this lecture. The mean of the Commonspace scores was 0.05, and the standard deviation was 0.423. Using this information, I could describe my data as follows. The mean of the Commonspace variable was 0.05 units. Observations deviated from the mean of 0.05 by 0.423 units on average.